Welcome back. And as I mentioned in my introduction video to elevation of boiling point, we're going to work out two problems. Okay, this is the first of the two problems. Okay, now you will see that in the first problem we are dissolving 147 grams of lactic acid. The formula is given in brackets. In 647 grams of cyclohexane. Cyclohexane is a liquid, which is a solvent in this case, so your lactic acid is the solute. The boiling point constant is given to you, and it's asking for the elevation of boiling point or boiling point elevation, right? So the formula is delta TB equals KB times M times I, okay? Now, first, what we have to understand is this lactic acid is your solute, right? It's usually less in quantity. And your cyclohexane is your solvent, which is usually large in quantity. So we have to find this information. And the boiling point constant is given to you, which is this, 2.79, right? Degrees Celsius over M. And this is the unit for this KB. And the Van Hoff factor, as I said, this is our compound that we are dissolving it in cyclohexane, right? Is there any metal in it? It's all non-metals, right? So I value is equal to 1, right? So this right here is 1. All right, that means we still have to find this molality, right? So I'm going to switch colors here so you can see my calculation for M. M is molality, right? Now, if you still don't remember from 170, so it's moles of solute over kilogram of solvent, right? All right. And a molar mass has to be found first for the lactic acid, right? So this is 72 plus 10 plus 16.5 is 80. So this is 90 plus 72 is 162 grams over mole. That's the molar mass of your lactic acid. So to find moles of solute, it's just 170 material, so it's 162 grams over 1 mole, which would be 147 divided by 162 is 0.907 moles. Okay, and we know the mass of the solvent, which is 647 grams, but we want it in kilograms, right? 647 grams over 1,000 grams is in a kilogram, so it's 0.647 kilograms. So molality would be 0.907 moles over 0.647 kilograms. Now, is this new? No, we have learned this, but we are applying the idea of molality in the context of the elevation of boiling point. So let me get my calculator here. All right, so it's 0.907 divided by 0.647, and that molality turns out to be 1.401 m. It's a lowercase m, right? All right, now we know this information is 1.401. Now we know all the information. We can solve for the elevation of boiling point. So let's get actually a different color. Let's get this one. So delta TB equals, KB is 2.79 times your molality is 1.401 times your Van Hoff factor is 1. Like I said, if the compound is not ionic, and what constitutes ionic? It has to be a metal and a non-metal. I don't think any of these are metals. They're all non-metal, so I is happen to be 1. Okay, so if we solve all this, 2.79 times 1.401 times 1, and the elevation of boiling point is 3.90 degrees Celsius. Okay, now what does this mean is water, okay, water boils at 100 degrees. That's a universally known information, okay? So if you add lactic acid to water and bring it to a boil, the water actually boils at 100 plus 3.90 degrees Celsius. This I'm just showing it to you just to see the effect of solute on a solvent, okay? The problem ends right here, okay? But water boils at 100, but when you add lactic acid, the water boils at 103.90. Remember this value, okay? We're going to go and solve the second problem and then compare this value to the value in the second problem where we are dealing in fact with an ionic compound. I've already given the clue, and then see if that value is less than this value right here or if it's more, okay? Then only we have a more conceptual understanding of what does all this mean on a larger scale. Just simply solving a problem will have absolutely no implication on your conceptual understanding of the concept. And this is much easier than your vapor pressure. But again, you do not have to remember this equation nor the Raoult's law equation that I have given. You just have to remember when to use mole fraction of solute or mole fraction of solvent, or when to use 2 parts to solve the total vapor pressure. Again, it's all in the video. You just have to watch, and watch again until you get it. If you don't understand, just ask me questions during class time. This way, we're both on the same page on what you know or what you don't know. All right, so stay tuned for the second problem video.